Good morning. I would like to thank the organizers for this opportunity. Today, I will discuss a general relativistic theory of electromagnetic field and show how it is related to quantum mechanics. Let me first quickly review Einstein's theory of gravitation, which can be summarized in two statements. First, matter tells space-time how to curve, and then space-time tells matter how to move. For example, the Earth causes space-time curvature around it. A test particle placed above the Earth is not aware of the space-time curvature. It travels at a uniform speed in its locally inertial frame, that is traversing equal distance in equal time. In other words, the test particle simply glides according to Einstein, but Newton interprets that the test particle is attracted towards the Earth and hence it is accelerating. Instead of the Earth and the test particle, if we have two charged particles, can the attraction or repulsion between them be explained by the space-time curvature? This is the question I have been trying to find an answer for the past 20 years. So to answer this question, let us first consider Maxwell's equations. Maxwell's equations explain the free space propagation accurately, but fail to explain the interaction with atoms or charges. Photoelectric effect cannot be explained by Maxwell's equations. Einstein had to use the concept of photons. Maxwell's equations do not provide the equation of motion for charges. It needs to be supplemented by Lorentz Force Equations. Reason is that Maxwell's equations for vacuum are linear and satisfy only one conservation relation. In contrast, Einstein's equations for gravitation provide the equation of motion for matter as well as provide the evolution equations for the gravitational field. Einstein's equations are nonlinear and satisfy four conservation relations. Later, I will show that the equations of motion for charges is built into Maxwell's equations if we take into account the space-time curvature. The problem of classical electrodynamics can be divided into two classes. First, the charge and current distributions are known and the resulting electromagnetic fields are calculated. Second, the external EM fields are specified and the motion of charged particles under the influence of EM fields are calculated. When these two problems are combined, as in the case of Bremsstrahlung, the classical treatment is a two-step process. First, the motion of charged particles in the external field is determined using Lorentz Force Equations, ignoring the emission of radiation by the charged particles. Second, Maxwell's equations are then solved to find the EM fields, taking into account the trajectory of moving charges. As pointed by Jackson, this way of handling problems in electrodynamics is of approximate validity, since the emitted radiation due to accelerating charges carries off energy and momentum and so must influence the subsequent motion of charged particles. A correct treatment must include the reaction of radiation on the motion of sources. A classical treatment of reactive effects of the radiation does not exist. I do not want to use quantum electrodynamics because I believe that quantum mechanics follows from general relativity after a few modifications to the theory and under certain approximations. I will discuss it in the next slide. Electromagnetic vector potential may be written in this form. Here, eta is some scalar, and it may be interpreted as the charge embedded in the field, although its dimension is different from the conventional charge. U mu is the for velocity and is given by this expression. Here lambda is a parameter along the world line. This u is a tangent vector to the world line. It has got 4 components. Lorentz gauge condition is given by this well-known expression. Here A is the 3-dimensional vector potential, and this can be written in the tensor form as here. So Einstein's summation convention is used here. In classical electrodynamics, one is free to choose either Lorentz gauge or any other gauge as long as the equations relating electric and magnetic fields remain invariant. However, in our model, Lorentz gauge condition is of fundamental importance because with the definition of 1, equation 2 is nothing but the conservation of eta. Parallel transport condition is given here. This means that the components of the tangent vector, that's u nu, do not change as a function of lambda. In other words, tangent to the world line at the current point is parallel to the tangent at the previous point. From equations 1 to 3, it follows that the product of EM vector potential is conserved. So there are 4 equations for nu 0 to 3. So we define an EM tensor in the following way, which is as a product of vector potentials. And in a locally inertial frame, we can rewrite 4 in terms of this EM tensor in this fashion. Here, comma denotes the conventional partial derivative. That's d over dx. Nu is written as comma here. So in curved spacetime, using Einstein's principle of equivalence, we replace this comma by semicolon. Here semicolon denotes the covariant derivative. So so-called comma goes to semicolon rule. Let me quickly review Einstein's equations for matter. This G here is the Einstein tensor, this R is the Ricci tensor, this is the Ricci scalar, and G is the metric tensor. And Einstein's equations for matter is G is alpha times T. Here T is the stress energy tensor for matter, which is given by this expression here. Here rho is the matter density and u mu is the for velocity here. This is for dust, and alpha is proportional to the gravitational constant G. The stress energy tensor T satisfies 4 conservation relations of this form, and Einstein's equations under the weak field approximations lead to Newton's theory of gravitation. For the EM field case, we modify Einstein's equations as here. Here left-hand side is the same as in Einstein's equations, the Einstein tensor G, and right-hand side, we instead of the stress energy tensor, we replace it by the electromagnetic tensor given by this equation here as an outer product of EM vector potentials, and kappa is some constant connecting these 2 tensors. And in terms of eta and for velocity, it can be written in this form. In fact, it has the same form as the stress energy tensor for dust. You see here, for dust, the stress energy tensor has got rho times product of 4 velocities. So in the case of electromagnetic field, we have the same form. Instead of rho, we have got eta square and product of 4 velocities. So eta square is playing the role of the matter density in the case of electromagnetic field. So we have seen before that electromagnetic tensor satisfies 4 conservation relations here. So we will show later that kappa is inversely proportional to Planck's constant h bar. So kappa is a constant connecting Einstein tensor and EM tensor. In the case of Einstein's equation for matter, the corresponding constant alpha is proportional to gravitational constant. So in the EM field case, kappa is inversely proportional to Planck's constant. Maxwell's equations in curved spacetime. In a locally inertial frame, Maxwell's equations are given by this equation here. So here, comma denotes the conventional partial derivative. G is the Minkowski metric tensor. We have got 4 such equations because we have got 4 components of the vector potential. And this is nothing but, this whole thing is nothing but the 4-dimensional Laplacian operator or wave operators. In curved spacetime, using Einstein's principle of equivalence, that is comma goes to semicolon rule, we replace these commas by semicolons, where semicolon denotes the covariant derivative. And this equation 13 can be expanded using Christoffel symbol in this form here. So the first term is still the same as here. It's the 4-dimensional Laplacian operator. And the other terms are some nonlinear terms. You can see that in the locally inertial frame, all the 4 components of the electromagnetic vector potential are uncoupled. Each of them are given by the wave equation. But here we have this wave equation part, but there is some nonlinear mixing of the EM vector potential components. Weak field approximations. We assume that the deformation of the metric coefficients due to the electromagnetic field is weak, so that G is eta plus kappa h. Here eta is the Minkowski metric, and kappa h is represents the small deviation of the metric due to EM field. Case 1. So let us assume that the vector potential A has only one component in the x direction. This corresponds to an electromagnetic wave with its electric field in x direction and magnetic field in y direction. So in this case, modified Einstein equations reduced to this form. The left-hand side is the wave equation, and the square of the electromagnetic potential is the source on the right-hand side. This corresponds to the part EM field telling space-time how to curve. So using this weak field approximation in the modified Maxwell's equation, we obtain the nonlinear wave equation in this form. Here left-hand side is the wave equation, and on the right-hand side we have nonlinear terms due to space-time curvature. This equation corresponds to the part space-time telling the EM field how to evolve. So these 2 equations are coupled. At each point along the world line, EM field tells space-time how to curve, and in turn, space-time tells EM field how to evolve. So equation 15 and 16 are Lorentz invariant. So now we use slowly varying envelope approximation on the nonlinear wave equation, and we substitute this in the nonlinear wave equation, and we ignore the second order term with respect to time, second order derivative with respect to time, to obtain the Schrodinger equation in this form, with a potential V that has self-dropping potential and other nonlinear terms. Using the vector potential A1, we can calculate the x component of the electric field and y component of the magnetic field. Mean momentum density of the electromagnetic field is given by this equation here. Here P3 is the z component of the momentum density. E1 tilt and H2 tilt are the slowly varying envelopes of the electric and magnetic fields respectively. And here the brackets are the expectation operators. And we can express this electric field and magnetic field in terms of the slowly varying envelope of the electromagnetic potential in this form. So multiplying the Schrodinger equation by d pi star over dz and integrating over the volume, we obtain the Lorentz Force equation in this form here. Here rho is the effective charge density and u is the three-dimensional velocity vector, and these are the expectation operators here. In classical electrodynamics, if you place a charge moving at some speed u in the magnetic field H, it experiences a Lorentz force. Only difference in our model is that we have the expectation operators here. Please note that we obtained Lorentz force equation from the modified Maxwell's equation, taking into account the space-time curvature. In classical electrodynamics, as I have mentioned before, Lorentz force equation does not follow from Maxwell's equations. Equation of motion. First, let us consider Einstein's equations for matter, which under the weak field approximation leads to Newton's law of gravitation in this form. Here, the deformation of the metric coefficient H00 could be identified with gravitational potential of Newton's theory. Next, let us consider Einstein's equation for EM field. Under the weak field approximation and slowly varying envelope approximation, it leads to Lorentz force equation. The difference is that we have expectation operators in our model. So both Einstein's equation for matter as well as this modified Einstein's equations give us equations of motion. So let us return to Schrodinger equation. So using this relation between kappa and Planck's constant and effective mass equal to defining effective mass equal to h bar omega over c square, we can write equation 33 as the Schrodinger equation in its standard form with potential V dash that is having a self-dropping potential in other terms. So interpretation of phi. So interpretation 1, phi is the slowly varying envelope of the electromagnetic potential A1, and this part, this imaginary part of phi and its gradient of phi star is the momentum density. That's E cross H star, that is the Poynting vector. So that is one interpretation. Second interpretation is that absolute value of psi square dx dy dz represents the probability that a photon is present in the region between x, y, z and x plus dx, y plus dy and z plus dz, with the probability current density being given by this expression, which is same as this here, the momentum density. So which one is correct? I go with interpretation 1. To summarize, Einstein equations with certain modifications and under certain approximation lead to Schrodinger equation. However, the statistical interpretation is open for debate. Phi is not the whole story. There are some hidden variables, namely metric coefficients, and their evaluation should also be taken into account. From Schrodinger equation, Ehrenfest theorem, if we use Ehrenfest theorem, we get the Lorentz Force equation in this form. So far, we looked only at one component of the vector potential, namely A1. In general, vector potential has 4 components, and under the weak field approximation, we get equations similar to Dirac equations. I will not discuss them today. Next, let us consider the linear modes of a rectangular cavity resonator. This is a hollow rectangular cavity with metallic walls. It may be noted that Max Planck studied the black body spectrum of this type of cavity, and he had to postulate that energy exchange between the radiation and the walls takes place as a discrete packet now known as photons. This was the beginning of quantum mechanics. Let us first consider the linear modes of this cavity. There are 2 types of modes. First one, transverse electric or TE modes, and the second one, transverse magnetic or TM modes. For the TE modes, the Z component of the electric field is 0, which means A0 and A3 are zeros, and A1 is given by this expression here. In general, A2 is not 0, but for the fundamental TE mode, A2 is 0, and I assume that Lx, Ly, and Lz are all equal to L, and from this it follows that Ky and Kz, they are equal to pi over L. Today I will focus only on the fundamental TE mode. Now let us analyze the quasi-linear TE modes under the weak field approximations. We have seen these equations before. These are the coupled equations describing evolution of vector potential and metric tensor deviations. We assume that the solutions of equations 16 is of the form. Here Gz is yet to be determined. For the linear case, that's when kappa is 0, Gz is given by a cosine function. In general, Gz is obtained by solving this nonlinear equation. Here beta is the propagation constant. The solution of 31 is shown here, labeled as semi-analytical. And plus in this figure shows the numerical simulation of equation 15 and 16 by using the finite difference scheme. The agreement is quite good, although there's a small discrepancy. In the absence of space-time curvature, that's when kappa is 0, beta is equal to Kz equal to pi over L. And angular frequency omega is C times K, where K is the wave number. And from this, resonant frequency of the cavity can be calculated and is shown here. And the resonant frequency is determined solely by L. However, due to space-time curvature, the frequency of the EM field undergoes a small shift depending on the energy stored in the cavity. Let the frequency detuning be delta F is F minus F resonant frequency, where F is the actual frequency of the EM field. So to obtain this figure, the frequency F, or in other words, the frequency detuning delta F is fixed. Here the x-axis is the distance z. Z equal to 0 corresponds to the center of the cavity, and z equal to 0.5 meter corresponds to the metallic wall. Blue line shows the field amplitude when delta F is 4.77 kilohertz, and red line shows the field amplitude when delta F is 47.7 kilohertz. As can be seen, as delta F increases, the peak amplitude increases, which means the energy stored in the cavity increases. Electrical and magnetic energy stored in the cavity are given by these expressions, and we define the effective mass as the total energy stored in the cavity divided by c square. This figure shows the effective mass as a function of the frequency of the electromagnetic radiation. Some of you may not be comfortable with the idea of defining mass for the EM field. Actually, it does not matter. We can consider the y-axis as the stored electromagnetic energy in the cavity, which increases with frequency. Here, plus show the semi-analytical results, and solid line shows the curve fitting. A good fit was found using this equation. Here, kappa is the constant connecting Einstein tensor and electromagnetic tensor. Equation 33 may be rewritten as a dispersion relation in this form. And if E is h bar omega and P is h bar k, and if kappa is given by this expression, here kappa is inversely related to Planck's constant, then this equation 34 becomes the well-known special relativistic equation connecting energy, momentum, and mass. For the linear case, that's when kappa is 0, we have energy is c times the momentum and mass is 0. So general belief that photon has 0 mass is the concept derived from linear Maxwell's equation. When space-time curvature is taken into account, photon behaves like any other particle, and this does not conflict with special relativity. Conclusions. The constant connecting Einstein tensor and the EM tensor is inversely proportional to Planck's constant. Modified Einstein equations under certain approximations lead to quantum mechanics. However, its statistical interpretation is open for debate. When the space-time curvature is taken into account, equations of motion are built into Maxwell's equations. They lead to Lorentz Force Equations. Thank you.